Hello everyone, thanks for being here. I'm Tongxin Li, a PhD candidate at Caltech, interested in AI and power system research. In this talk, I'll be introducing a learning augmented linear control problem. I'll be talking about joint works with my advisors and a bunch of collaborators. In the last decade, we have seen the advances of many learning and AI techniques. They have achieved the state-of-the-arts in many decision-making problems. However, they cannot be directly applied to many real-world applications because they often do not have worst-case guarantees on the performance. For example, there are domains that safety really matters, and you can trick deep learning models using adversarial noise. And indeed, in many practical control systems, there are such worst-case scenarios that we need to be very careful. Let's first consider a quick example. Right? We know that there are a couple of machine learning and AI predictions available, and they are ready for us to use. So the question is, how can we combine them into a control system, right? Well, if we trust predictions, there won't be any issues, but there will be problems if the predictions are far from truth. In fact, often we know nothing about the quality of the black box AI predictions because there are no guarantees. Under this broad regime, recently finding a better way to integrate the predictions into online decision-making problems has brought tons of interests, including ski rental, convex body chasing, and so on. The work I'm going to talk about falls into this big category. For this kind of online problems, given predictions, there is always a trade-off between being conservative and being aggressive. For example, if we ignore the predictions, the best-known online algorithms can always give us a constant compare ratio. However, if there is an algorithm that trusts predictions, right, it is possible to have an even lower compare ratio if the prediction error is small. But the money we pay is when the prediction error becomes large, things can be messed up. And the general goal of this type of problems is to design some meta algorithms so that we can change parameters depending on whether the prediction error is small or large correspondingly. To give you an example, let's consider there is a robot that needs to track an unknown trajectory. We get some predictions about the future trajectory from an AI oracle, but we are not sure if the predictions are good or not. Let's use MPC as a controller, which is commonly used in many applications. We see that when the predictions are perfect, it works super well. But if there are errors in the predictions, things can be arbitrarily wrong, despite there are some robust MPC methods trying to fix this issue. As I will go into the details later, arbitrarily bad predictions can still destroy the controller, so we need a different method. Let's consider this general robustness and the consistency trade-off using a specific simple linear system that we have in Control Class 101. This is the model we consider. We have linear dynamics with a sequence of adversarial perturbations W. We can also access to a sequence of predictions of perturbations, denoted by W hat. We assume this prediction does not change over time, but our analysis can be easily carried out to the general case. We also assume A and B here are known to the controller. The goal is to minimize a quadratic cost function. We assume some common assumptions on the system matrices as well. There are many existing control policies designed for the simple linear model, such as robust and tube-based MPC. But the thing is, those policies require bounded error, and often they do not have comparison guarantees. So the question again is, if you can find a policy that works well, even if the predictions are totally untrusted, and the prediction error becomes very large. The performance metric we consider is the compare ratio, defined as the ratio between our algorithm cost and the optimal cost, knowing the true perturbations in hindsight. Remember, we want to be conservative if the prediction error epsilon here is large and vice versa. So the question is, what's the definition of a prediction error epsilon here, right? So we define it as a norm of weighted sum of the difference between WT and WT hat. There are intuitions why we define it this way instead of just calculating the difference between the two vectors. This is because first, the impact of error in prediction at each time differs. The impact from the long future on my current system is smaller than that from the near future, right? Moreover, this is in fact a term that characterizes the total error in the actions caused by the error in the predictions, but I will not show you the details here. There are some toy examples that can be modeled by our system. One is the robot tracking I showed earlier, and we have the velocity and the locations of the robot being the state, and the unknown trajectory is modeled as system perturbations. Similarly, on the right-hand side, we can also use the acceleroted perturbations to model arrival patterns of EVs, and the charging and discharging of EVs can be approximated using a linear system as well. Moreover, LQC is very common in different applications in power systems, including frequency and voltage control with a linearized power flow model. So how to design a minor policy for this model, for this LQC problem, right? Well, let's first revisit the model predictive control scheme again. We know that it works well when the prediction error epsilon is small. Moreover, we can write down the optimal solution given by MPC explicitly as a linear function of the system state and predictions. What if we combine MPC that makes use of AI predictions with another linear policy that ignores the predictions, right? I would like to note here, so the second policy, right, on the second line, if you drop the predictions here, this linear policy is actually exactly the optimal linear quadratic regulator with Gaussian perturbations. To be more specific, right, what if we introduce a trust parameter lambda and create a convex combination of the two policies above? Their convex combination implies the policy in the middle with an additional trust parameter lambda, and we call this lambda a trust parameter because it characterizes our confidence on the predictions, and we call this new policy a lambda confident policy. And increasing this trust parameter means that we trust predictions and vice versa. Setting lambda to be 0 or 1 recovers the purest two policies that we have combined. It's worth noting that the lambda confident control policy can be viewed from a different angle as an MPC policy by plugging a trust parameter in front of the predictions to indicate our confidence level. So we have, in the constraint of the MPC, some additional term lambda here and the prediction here. So it's basically a special case of the MPC framework. For this lambda confident control policy, we can prove an upper bound on its compatibility ratio. And this gives us a trade-off basically between robustness and consistency for our LQC problem. We can see that if epsilon is small, the second part on the bound dominates, but when epsilon becomes large, the compare ratio is upper bounded by a linear function of epsilon. And if you fix the prediction error, we can find the best corresponding trust parameter lambda, and you will see this is very helpful in the later part of this talk when we're gonna prove the main results. This is a realistic worst-case compare ratio experiment. So you can see that when the prediction error is small, so the compare ratio curves are nonlinear, and when error becomes large, as indicated by our theorem, the linear term in the compare ratio bound dominates, and the curve becomes that of a linear function. So far, as a summary, we have found a meta control policy, that is the lambda confident control, to give us a spectrum of compare ratio bounds by varying the values of lambda as most. So this is basically most existing works on this kind of learning augmented online algorithm did for multiple or various online decision making problems, right? But we're still not very quite satisfied because it is not clear how we can set the value of lambda optimally, right? Because we know nothing about the prediction error at the beginning. Therefore, it is a very natural question to ask that if we can actually find a better scheme that can achieve the best compare ratio when the prediction error changes. Meaning that, can we actually basically obtain a lower envelope of those curves corresponding to using fixed lambda, right? So this is basically the optimal case we're looking for. To do this, we use the idea in online learning because we can explicitly write down the difference between the algorithm cost and the optimal cost, and it is a quadratic function of the trust parameter lambda. We can minimize this based on previous observed perturbations and predictions. Therefore, minimizing this cost gap, we can find a lambda t here, which is an optimal fixed lambda for the previous t-1 time steps. This gives us a follow the leader design and is only based on previous information. Furthermore, the computational complexity is small because we only need to compute a few more new terms at each iteration. Finally, the expression of lambda t looks complicated, but we see that if w hat and w are getting closer, meaning that the predictions are more trustful, then the denominator and numerator will also be more similar, so lambda t will be closer to 1. This means we trust the predictions, right? Combining those pieces together, we end up getting our self-tuning control policy. At each time, we compute lambda t based on our optimal online learning solution. Then we use this lambda t as a parameter in the lambda confidence control algorithm, update the next state, and this process repeats. Again, the term eta here for time t can be computed from its catch for time t-1. Therefore, the computational complexity is low. Using the previous upper bound on lambda confidence control policy, we can actually obtain an upper bound on the compare ratio of the self-tuning control policy as well. The upper bound consists of two additional terms. The first one is a function of prediction error epsilon. If epsilon is 0, this term becomes 0. The interesting thing is, if epsilon becomes very large, this nonlinear term is still bounded, right? The second term measures how fast, the second term basically measures how fast w and w hat change. If they change really fast, it is hopeless to use online learning to find the best lambda. But in many applications, the perturbations change slowly. For example, in the robot tracking problem, the unknown trajectory is continuous, and the robot cannot jump from a point to another one that is far after a second. And moreover, many AI methods, they can be regularized to minimize the variation of their perturbations, the predictions of perturbations. So it is hopeful to have a bounded compare ratio in many different applications satisfying those kind of conditions. To better understand the theorem, let's check out our experiments for EV charging. In this figure, we see that indeed by varying lambda, we obtain trade-offs between consistency and robustness. Especially if we zoom in and check out the left figure, for different prediction errors, there are different optimal lambda values, right? And we see that our online self-tuning policy is able to adjust itself regardless of what the prediction error is, and its compare ratio scales in a nonlinear way as indicated in the theorem. Similarly, we observe that it works well for robot tracking, right? So the y-axis here means compare ratio, and the left figure is kind of like a zoomed in version for the low noise regime of the right-hand figure, right? As a brief introduction, the proof of the main results is a nice combination of our first compare ratio bound for lambda confidence control policy and the convergence of lambda t. So first, by optimizing the upper bound in the first theorem, showed in earlier slides, we obtain the nonlinear term in epsilon, and then we can bound the convergence of lambda t by the variations of w and w hat, which can be further used to bound the regret as a difference between the algorithm cost when we use the time varying lambda t and the algorithm cost when we use the optimal lambda. Putting them all together completes the proof. So we demonstrate the convergence of lambda t and the performance of our policy, again in the robot tracking problem. We first consider the case when prediction error is low. We see that as time goes by, lambda t converges pretty fast to the optimal lambda, and our policy gives a much smaller tracking error compared with the optimal linear policy, which is the linear quadratic regulator, and that does not make use of the prediction at all. Moreover, when the prediction error becomes high, we can see that lambda t converges quickly to a different optimal lambda, and our policy still works well, but MPC in this case can be arbitrarily bad. And we also have a summary of, for different noise regime, how this lambda t converges and the corresponding trajectory, and how the trajectories behave for, when we have different versions of error. And you can see it works pretty well for other cases. Finally, even for nonlinear dynamics, such as the carpool problem, we can verify our policy still works well, and it tries to give the best reward no matter how the prediction error actually changes. So this is a signal, actually, if you have a linear approximation of some nonlinear dynamic, you can still hopefully use the method, and it can still work. So let's talk about future directions. And the first question is obviously, if you can show the bound in our result is actually tight. Again, so we consider only the predictions about the perturbations, but what if you have some predictions about the dynamics, because sometimes you don't know the matrices A and B for the system, right? What if you have predictions about them as well? And what can you say about this case? And another extension is to generalize to general nonlinear dynamics, and and also more general form of predictions, such as we just get some deep RL policies at some black box, and what can we do in this case? And I will just talk a little bit more about this because this is kind of interesting, and this is our original model, right? We have the AI predictions submitted to the controller. But what if we have, in the general case, only deep RL policy as some black box, and you can only consider this as a function of the state, and you know nothing about this, right? You don't know the details of the neural networks. You know nothing about the what's inside this black box. And in this case, what can you do, right? Can you still consider a linear combination or a convex combination of the policies by introducing a trust parameter? Well, in general, the answer is probably no, because we know that the space of linear stabilizing policies is non-convex. So if we combine two policies linearly, we may end up getting an unstable controller. And how to design a better parameterization for RL policies or a better scheme to combine policies is a question worth exploring in the future. This is the end of my talk. Thanks again for your attention, and please feel free to ask me any questions by sending me some emails. And bye.